Okay, for this remaining part, okay, we're going to be looking at using eigenvalues and eigenvectors to solve for systems of differential equations. And the notations I will be using will be somewhat different from what is in the textbook. And but still, you're going to be looking at arriving at the same results. And let's say that if you have a system of equations where we have, say, like in this set, we have for two equations. We have the first one where we're going to have the first order derivative of y sub 1 is equal to 2 times y sub 1. And we have that the first order derivative of y sub 2 is equal to y sub 2. And if we put this system up where we can utilize matrices, so putting in terms of both y sub 1 and y sub 2, we can say that we had the first order derivative of y sub 1 is equal to 2 times y sub 1 plus 0 y sub 2. And for the first order derivative of y sub 2, we can say that is equal to 0 times y sub 1 plus 1 times y sub 2. And for this two equation system, we have with the identity matrix, so we have this in the 2 by 2 array. And likewise, we have for the coefficient matrix, to cover what we have in both y sub 1 and y sub 2, we have 2, 0 in the top row, 0, 1 in the bottom row. And setting things up, now we're going to be looking at the determinant of lambda times I minus A. And so for the difference here, we come out to the matrix lambda minus 2 and 0 for the top row. And in the bottom row, we have 0 and lambda minus 1. And looking at establishing the determinant. So that is going to be the product of lambda minus 2 times lambda minus 1, and establishing the characteristic equation. So we have upon setting the determinant equal to 0, and we have upon utilizing the zero product property, we're going to have the first eigenvalue, or what could be the first eigenvalue, we'll have that equal to 2. And if we have the first eigenvalue at 2, well, we're going to have with the other eigenvalue, this will come from lambda minus 1 set equal to 0, where we have lambda sub 2 is equal to 1. And looking at establishing what we will have for the eigenvectors, and just a little departure from the textbook notation, but we have in the big picture, so we have lambda I minus A times what's going to be the eigenvector y in the general case. And we'll be looking for two eigenvectors, the first of which we will have to comply with the eigenvalue of 2, and the second eigenvector which will comply with the eigenvalue of 1. And again, so for what we have at the eigenvalue equal to 2, so we have for lambda I minus A, so you have 2 minus 2, which is 0, 0, 0, and then we have 2 minus 1, which is 1, and we have representing the eigenvalue y. So we have a 2 by 1 array where we have y sub 1, y sub 2, and again we have equal to 0 where we have in the 2 by 1 matrix format. And just taking what we have and putting in terms of an augmented matrix. So you have 0, 0, 0, 0, 1, 0, and in the reduced row echelon form, which will be attained by flipping the rows. And this is going to signal from 0, 1, 0 at the top that y sub 2 is equal to 0. And there is no statement where we have y sub 1's representation isolated. And so that is going to be a free variable. And so we let y sub 1 be equal to t. So we have with the first eigenvector, for this y sub 1, again, that is equal to y sub 1 and y sub 2. And again, y sub 1 we have at t, y sub 2 is at 0, and factoring out, so we end up with t times the basis, which is going to be 1 and 0. And that's going to be carried over in the determination of what we have in our solutions for y sub 1 and y sub 2. And for the other eigenvector, so if we let the eigenvalue be set equal to 1, and so for what we have for lambda I minus A, so we end up at negative 1, 0, 0, and then we have 0, 0, 0 on the bottom, and the reduced row echelon form, which we have to result from taking the opposite sign of the top row. And with the 1, 0, 0 across, we have y sub 1 is equal to 0, and this time it is y sub 2 that is free. And letting y sub 2 be equal to t, So we're going to have for the second eigenvector, okay, it's going to come out equal to, and we have upon substituting, we have 0 and t, and factoring out t, we have t times the basis, which is going to be 0 and 1. And so we're going to carry over the basis for the first eigenvector as well as that for the second eigenvector, and just in the overall big picture. So we have for the solution set in y, that's going to be equal to the constant times the eigenvector times e to the eigenvalue times t degree. And breaking this up, okay, to a linear combination, okay, so we have that the set y, we have c sub 1 times the first eigenvector times e to the first eigenvalue times t degree, and you have plus c sub 2 second eigenvector times e to the second eigenvalue times t degree, and taking what we have for the basis of the first and second eigenvector. So you have c sub 1 times 1, 0, and we have e to the lambda sub 1, which is at 2 times t, and we have plus c sub 2 times the second eigenvector basis, 0 and 1, you have times e to the lambda sub 2, which is 1 times t, and so just clustering together. So you have with the top layer, we have c sub 1 e to the 2t, bottom layer, we have c sub 2 times e to the t, and what we have at the top will be what we have for y sub 1, which is going to be c sub 1 times e to the 2t, and for what we have at the bottom, we're going to have y sub 2 equal to c sub 2 times e raised to the t. And looking at another set, say we have also with a two equation system, so we got the first order derivative of y sub 1 is equal to 1/2 of y sub 1, and going ahead and putting in terms of both y sub 1 and y sub 2, so we have 1/2 of y sub 1 plus 0 y sub 2. For the second order derivative of y sub 2 equal to 1/8 of y sub 2. So just go ahead and express this as 0 y sub 1 plus 1/8 of y sub 2. And that is just to ensure that we have the right coefficient matrix. So we have A is going to be 1/2 0 at the top, 0 and 1/8 on the bottom. And again, the identity matrix have 1 0 0 1. And carrying out what we have for the backdrop to the result in the determinant. Okay, so we have lambda I minus A, and this will translate to lambda minus 1/2 0, and then we have at the bottom 0 and lambda minus 1/8. And so the product of these binomials that we have in lambda will form the characteristic equation, and setting the equation equal to 0, and by the zero product property, we're going to have our eigenvalues at 1/2 as well as 1/8. And going back to the setup in the determination of what we have in the eigenvectors. So looking at the first eigenvector, if we set lambda equal to, again, the first eigenvalue at 1/2. Okay, so we're going to have for lambda I minus A, we're going to have 0 0 0 3/8, and again times the first eigenvector, and we have equal to 0 represented by the 2 by 1 array with the zeros, and just expressing what we have here in augmented matrix terms. So you have 0 0 0 across, and in the bottom row we have 0 3/8 and 0, and putting in terms of the reduced row echelon form, we have 0 1 0 at the top, and this is going to signal y sub 2 is equal to 0, and we have zeros at the bottom, so the system is consistent. But we have y sub 1 is going to be a free variable, and so we're going to set this equal to t. And so for the first eigenvector, okay, we're going to have at t and 0, and factoring out t, we're going to have t times the basis, which will be 1 and 0. And if I apply the same thing in the setup now with lambda equal to 1/8, and we're going to have in the setup, okay, and just expressing in augmented matrix terms, we're going to have the reduced row echelon form to result with y sub 1 equal to 0, and with y sub 2 as a free variable, and letting y sub 2 be equal to t, we're going to have for the second eigenvector, we're going to have y sub 1 at 0, y sub 2 at t, and factoring out t, we have times the basis, 0 and 1. And just looking at what we have for the system set, solution set in y, so we have with our combinations regarding what we have in the two eigenvector eigenvalue system. Okay, so we have c sub 1 times the first eigenvector basis, which we have at 1, 0 times e to the first eigenvalue times t, and then we have plus c sub 2 times the second eigenvector basis times e to the second eigenvalue times t. And so combining together, we're going to end up with y sub 1 at c sub 1 times e to the 1/2 of t, and y sub 2 equal to c sub 2 times e to the 1/8 of t. So we've had a couple of two equation systems. And if we go with a four equation system, okay, so we have y sub 1 prime, y sub 2 prime, all the way down to y sub 4 prime. And we have respectively equal to 7 y sub 1, 9 y sub 2, negative 7 y sub 3, and negative 9 y sub 4. And so we're going to have with our identity matrix, okay, and so we have running diagonally, okay, that should be a 1 at the bottom. So we're going to have a diagonal array of 1s in the midst of zeros. And for the coefficient matrix, they have 7 y sub 1 exclusively as the only non-negligible term. Next row we have only 9 y sub 2. Next we have negative 7. And then the last we have negative 9. And for lambda I minus a, so you're going to have a diagonal array of lambda minus 7, lambda minus 9, and lambda minus negative 7, which will translate to lambda plus 7. And for lambda minus negative 9, which is going to translate to lambda plus 9. And for the determinant, okay, so we have with this 4x4 array, ultimately, since we have all these zeros in the midst, this is going to condense to lambda minus 7 times that minus 9 times lambda plus 7 times the quantity of lambda plus 9. And we have with our characteristic equation, we're going to have these four binomials in the variable lambda set equal to 0. And we have with the zero product property, okay, we're going to have lambda sub 1 equal to 7. From the second factor, we have lambda sub 2 equal to 9. And for the third eigenvalue, we have at negative 7. And for the fourth and last, we have negative 9. And just going through the process of the determination of the eigenvectors. So for what we have in correspondence, if we let the first eigenvector be 7 and running it through what we have in the process. So for lambda I minus a, you're going to have zeros, but running diagonally from the upper left-hand corner, we have 0, negative 2, 14, and 16 times our first corresponding eigenvector is equal to 0, which will be symbolized in this 4x1 array. And putting in terms of an augmented matrix and applying the reduced row echelon form. And we're going to have y sub 2, y sub 3, and y sub 4 equal to 0. And since there's nothing to signal that y sub 1 is isolated, since we have only zeros in the first column, y sub 1 is going to be a free variable, and we can set this equal to t. So for the first corresponding eigenvector, okay, with y sub 1 at t, everything else at 0, we have upon factoring out t, we have for the first eigenvector basis, that is going to be 1, 0, 0, and 0. And going through the second eigenvalue, having this set to 9, and we're going to have in the setup, we're going to have going diagonally 2, 0, 16, and 18 in representation of lambda I minus a. And again, we have times the second eigenvector is equal to 0, and setting up what we have in the augmented matrix layout, we have upon applying the reduced row echelon form. Okay, so we're going to have y sub 1, y sub 3, and y sub 4 equal to 0. And this time y sub 2, since we have only zeros in the second column, okay, y sub 2 is going to be free, and so we can set y sub 2 equal to t. And so for the second eigenvector, we have 0t, 0, and 0, and factoring out the variable t, we're going to have the basis at 0, 1, 0, and 0. And with the third eigenvalue, if we set this equal to negative 7, and we have running diagonally in representation of lambda I minus a, we'll end up with negative 14, negative 16, 0, and 9, and multiplying the third eigenvector, and then we have equal to 0. We can have in the representation of the system, once again, the formation of the augmented matrix. And so looking at what we have and putting in terms of reduced row echelon form. So the top row signifies that y sub 1 is 0. Second row, we have y sub 2 equal to 0. Next row, we have this time y sub 4 equal to 0. And the third column has exclusively zeros. And so y sub 3 is free, and we're going to set that equal to t. So for y sub 3 at t, we have for the third eigenvector, so we have 0, 0, t, and 0. And factoring out the t, we have 0, 0, 1, 0 for the basis. And we have with the last eigenvalue at -9. So we have for the lambda I minus a, we have from the upper left-hand corner and running diagonally in midst of the zeros surrounding. So we have -16, -18, 2, and 0. And again, we have times the last eigenvector. We have equal to 0. And from the augmented matrix setup, okay, and putting in terms of the reduced row echelon form, so y sub 1 is 0, y sub 2 is 0, y sub 3 is 0, and this time we have y sub 4 to be the free variable, and we can set this equal to t, and putting back, so we have for the last eigenvector, we have y sub 4 equal to 0, 0, 0, and t, and factoring out t, so we have t times the basis, which we will have at 0, 0, 0, and 1. And for what we have in the solution set for y, again, we have in the big picture, we have c times the eigenvector y times e to the eigenvalue times t degree. And breaking up what we have in the statement into terms that we have a linear combinations regarding, c sub 1, y sub 1, e to lambda sub 1 of t all the way out to the fourth set. So you have c sub 1 times the first eigenvector basis times e to the 7t, and got c sub 2 times the second eigenvector basis times e to the lambda sub 2 of t, which will be 9t, and they have plus c sub 3 times the third eigenvector basis times e to the -7t, and we have plus c sub 4 times the fourth eigenvector basis times e to the -9t, and combining the terms, so we have for the set, we have what's going to be y sub 1 is equal to c sub 1 e to the 7t, y sub 2 is going to be c sub 2 times e to the 9t, and we have followed by y sub 3 is equal to c sub 3 times e to the -7t, and we have y sub 4 equal to c sub 4 times e to the -9t. And we have also looking at solving for systems of linear differential equations. And let's say that if we have, in the case of the first order derivative of y sub 1, we have y sub 1 minus 4y sub 2. And the first order derivative of y sub 2 is equal to 2y sub 2. So again, we have the identity matrix at 1, 0, 0, 1. And the coefficient matrix we're going to have at 1, -4, 0 due to the missing y sub 1 term, and 2 in reference to 2y sub 2. And for lambda I minus a, so we have lambda minus 1, and subtracting -4 is going to be a +4. Bottom row we have 0, and then we have lambda minus 2. And for the determinant, okay, we're going to be looking at the product of lambda minus 1 quantity times the quantity of lambda minus 2. And putting what we have in terms of the characteristic equation. So we have both of these statements, okay, multiplying and setting to 0. And we have with the zero product property from lambda minus 1, let that be in reference to the first eigenvalue. So we'll have the first of these at 1, and with lambda minus 2 leading up to the second determined eigenvalue. So we're going to have lambda sub 2 equal to 2. And for what we have in the setup, in the determination of the eigenvectors. So lambda I minus a, if we have lambda sub 1 equal to 1, so you got 0, 4, 0, -1 times the first eigenvector equal to 0, and putting what we have in terms of an augmented matrix and placing in reduced row echelon form terms. Okay, so we end up with 0, 1, 0, so this will signal that y sub 2 is equal to 0, and there's exclusively going to be zeros in the first column, so this will signal that y sub 1 is free, and we can go ahead and set this equal to t. So for the first eigenvector, we have t and 0, and factoring out t, we have times the basis, which will be 1 and 0. And for the second eigenvector, we have this set up for lambda I minus a, so we have 1, 4, 0, 0 times the second eigenvector is equal to 0, and so we have for the augmented matrix, that is already going to be in reduced row echelon form terms. So you have 1, 4, 0 at the top, and this will signal that y sub 1 is equal to -4, y sub 2. and y sub 2 is going to be a free variable, and we can set this equal to t. And so we're going to have y sub 1 equal to negative 4t, and just filling in for what we have for the second eigenvector. So again, we have y sub 1 at negative 4t at the top, y sub 2 at t on the bottom, and factoring out t, we have the basis at negative 4 and 1. And just going back to our solution system, okay, so we have, again, two eigenvectors and eigenvalues, and putting in terms of the linear combinations. So you got c sub 1 times the first eigenvector basis at 1, 0 times e to the 1t, and then we have plus c sub 2 times the second eigenvector times e to the 2 times t. And then just combining, so we have for the system, we have c sub 1 e to the t minus 4 c sub 2 e to the 2t, and we have at the bottom, we're going to have only c sub 2 e to the 2t. So we have for this system, we'll have y sub 1 is equal to c sub 1 e to the t minus 4 times c sub 2 e to the 2t. And for y sub 2, we have c sub 2 times e raised to the 2t. And let's say that for what we have in 28, we're going to have for this 3 equation system. So you're going to have for the identity matrix, 3 by 3 array. And for the coefficient matrix, so we're going to have negative 2, 0, 1. From the second equation, we have 0, 3, 4. Last equation, we have 0, 0, and 1. So we have only y sub 3 present. And for lambda I minus a, we're going to have, again, lambda plus 2, 0, negative 1. Next row, we're going to have 0, lambda minus 3, negative 4. Last row, we have 0, 0, lambda minus 1. And just taking what we have for the evaluation or the determination of the determinant of lambda I minus a, and go ahead and put these parallel bars down. And so we have for the determinant, okay, we have lambda plus 2 quantity times the quantity of lambda minus 3 times that of lambda minus 1. And we have, upon setting this equal to 0, we have the establishment of our characteristic equation. And looking at these factors in order from left to right, so we can say that for the first eigenvalue, that will be at negative 2, second will be at 3, and the third and last will be at 1. Okay, so after the establishment of the eigenvalues, okay, so for the first eigenvalue at negative 2, so for lambda I minus a, we're going to have 0, 0, negative 1 for the top row, 0, negative 5, negative 4 for the middle, 0, 0, negative 3 for the bottom row, and again, just with the system set equal to 0 and expressing in terms of an augmented matrix. And for the reduced row echelon form, okay, we're going to have the top row signifies that y sub 2 is 0. Next row we have y sub 3 equal to 0, and last row we have zeros running across. And since we have the first column to consist of only 0, this signals that y sub 1 is going to be free. And so we're going to have that y sub 1 is equal to t. And so for the first eigenvector, we have t, 0, 0, and factoring out t, we're going to have the basis of the first eigenvector to be 1, 0, and 0. And we have, going through the same process with the second eigenvector, I should say, for the determination of the second eigenvector, if we set lambda sub 2, that is the second eigenvalue, let that be 3. And going through the motion and putting in reduced row echelon form, we're going to have the top row is going to signal that we have y sub 1 equal to 0. Next row, we have signaling that y sub 3 is 0. And again, we have just zeros across, signaling that we have a consistent system. And since we have the second column to be consisting of only zeros, this means that y sub 2 is free, and we set that equal to t. So for y sub 2, we have 0, t, and 0. And factoring out t, we have the basis at 0, 1, and 0. And for the third eigenvector determination, if we let the third eigenvalue be at 1, and again, going through the motions, okay, so we have taking 3, 0, negative 1, 0, 0, negative 2, negative 4, 0, and zeros across, and translating in terms of reduced row echelon form, we're going to have the top row at 1, 0, negative 1/3, and 0. So we'll have signaling that y sub 1 is equal to 1/3 of x sub 3. Next row we have 0, 1, 2, 0, and this will signal that y sub 2 is equal to negative 2 times x sub 3, and there's nothing whereupon we have y sub 3's representation to be isolated. So this is going to be a free variable, and if we let that be equal to t, well, y sub 1 is going to be 1/3 of t, and y sub 2 is going to be equal to negative 2t. And so just for the third eigenvector, okay, so we're going to have, upon factoring out t, now you could keep these values for the basis, but if you want to get rid of the fractions, okay, we can go from 1/3, negative 2, and 1 is the basis to instead, say if I multiply by 3, we're going to have 1, negative 6, and 3. So we just have this as the basis, but you could have 1/3, negative 2, and 1 as well. And for what we have for the solution system, okay, so for cy e to the lambda t, breaking this up, so we're going to have for the first part, we have c sub 1 times the basis of the first eigenvector times e to the degree of the first eigenvalue times t. So we have, for the next, we have c sub 2, second eigenvector basis times e to the, what's going to be 3t, since 3 is the second eigenvalue. And we have plus c sub 3 times the third eigenvector basis times e to the t, since lambda sub 3 is at 1. And combining what we have here, we have for y sub 1, this will come from the top layer, where that is going to be c sub 1 e to the negative 2t plus c sub 3 times e to the t. And then we have for y sub 2, we have c sub 2 e to the 3t minus 6 times c sub 3 e to the t. And we have for the third y, okay, we have y sub 3, and that's going to be only equal to 3 times c sub 3 times e to the t.